Good morning or good afternoon, everyone, depending on where you're joining us from, and welcome to today's webinar. My name is Garrett from Business Review, and I'll be your host today. It is our pleasure to have Biogelx with us today, who will be presenting this webinar titled, The Use of 3D Bioprinting to Achieve Uniformity and Reproducibility of In Vitro Skin Models. Today's guest speakers are Chris Allen, Development Scientist at Biogelx, Jose Manuel Baena, CEO, Breca Healthcare and Regemat 3D, Mario Juarez Rodriguez, Research Associate at the Platform for Tissue Engineering and 3D Printing, La Paz University Hospital. I'd like to welcome you to our webinar platform On24. You'll notice that this webinar is browser-based, so if you do disconnect for any reason, please just click on the link that you received via email to rejoin the session. In order to ask questions, you can send them in via the questions widget. Just type them into the box at the top left-hand corner of your screen and click Submit. We'll allocate some time at the end of the session to address any questions or thoughts that you may have. Please use the yellow Help widget if you require any assistance, and you can move, resize, and maximize any of the windows in front of you to get a better view of the slides. But now, please allow me to welcome Chris.
Hi everyone, and hi Garrett. Thanks very much for hosting the webinar, and thanks to Business Webinars for having us. For everyone that's tuning in online. So as Garrett introduced, my name's Chris. I'm a development scientist here at Biogelx. Here to give a quick overview of our biomaterials and particularly the bioinks applications that they have in the lab before handing over to Jose and to Mario, who can tell a little bit more about some of the applications they've been working on. As Gad said, there will be an opportunity for questions at the end. If there's anything that we don't go around to cover in today, then I will leave some contact details up at the end of my presentation, so feel free to get in touch either through the website or through the email address info@biogelx.com. So I thought it best to start with a short introduction to myself. We spun out from the University of Strathclyde to commercialise some technology developed by Professor Ryan Yulin. The technology is based on short peptides, which assemble into fibres and ultimately form gels that can be used for 3D cell culture and for bioprinting. Of course, the relevance of cell culture in a 3D environment is that it more closely resembles native conditions in vivo. The possibility to construct some of these 3D structures using bioprinting has really developed that idea a little bit further in research. Biogelx have a range of products all based around the core technology that was spun out of Professor Yulin's lab. And one of the key benefits that we feel of the Biogelx materials is the ability to tune the mechanical properties of the gel and also to choose some of the biochemical in the material, as we now have a range of products with different functional motifs attached to them. So at the risk of becoming a little technical, I thought it was probably best to go over the core technology that all of these products are based on. And really what's key to these materials is this two-component system of a gelator and a surfactant peptide, each of which have an FMOC handle. When these precursors are dissolved in water, they form nanoscale fibres, such as the one shown on the right here, through a process that we call cooperative assembly. These fibres are then stabilized through non-covalent interactions, some of which include pi-pi stacking of the aromatic FMOC groups, which is why it's important to have those hand peptides there. The way the fibres assemble, they're arranged with the more polar surfactant peptide towards the surface of the fibre, and this gives us a more polar surface for cell adhesion to the fibres that are formed. Crucially, at this stage, once the fibres are formed, the material is not truly a gel, it's still a flowing solution with relatively low viscosity, and we refer to this as the pre-gel state. The first in the two-step gel forming process that our materials undergo, and that's shown in this slide here. So the first step, as I just mentioned, you add deionized water to the peptide precursors and form this pre-gel solution through the cooperative assembly process. Then in the second step, a gel is formed by cross-linking the fibres that were formed in step one. Now, because both peptide precursors are free carboxylic acids, the cross-linking mechanism happens through introduction of a suitable divalent cation. And in this case, the cations that we're interested in are calcium 2+ ions, which are present in cell culture media. So through addition of cell culture media to the pre-gel solution, we produce gels such as the one shown at the right here, 2D culture. This gel state is typically analysed by rheology, trace that we can see on the left here. And you can see that the elastic modulus, the blue line there, which is essentially the solid component of the material, predominates over the viscous modulus, the red line there, which is more linked to the liquid component of the material. In the centre here, you can also see the image, which shows the nanoscale fibres formed by this material. What does this mean in person when you're in the lab? Well, all of our products are provided as lyophilized, amorphous powders, helpful for solubility. So those two steps that we've just discussed previously, you add deionized water at room temperature, and with a little bit of mixing, either by vortex or with a pipette, you should obtain a clear pre-gel with relatively low viscosity, such that it can still be transferred by pipette. In the second step, the addition of cell culture media or another source of cross-linking cations causes gelation, and in this instance, in the picture shown here, pink colour is due to pH. The gel, as shown at the image at right, has a nanoscale fibrous morphology, and that's similar to the extracellular matrix environment. And one of the benefits of these materials, we feel, is that from start to finish, gel preparation is performed at neutral pH and either room temperature or at 37 degrees. Because the process is based on these fibre assembly and cross-linking steps rather than manipulation of temperature conditions. So with the lyophilized powder, it's possible to tune the stiffness of these materials simply by changing the concentration of the powder used. Essentially what we're doing here is increasing the density of that nanofiber network that we talked about. And this can be important in research applications because different tissues in the body exert different strains on the cells that are contained in that site. See in the diagram on the right hand side there, moving from softer tissues such as brain through to more stiff environments, including cartilage and bone. That's something that can be mimicked in your 3D cell culture material simply by changing the concentration of the powder that you use to make these gels. In addition, the mechanical characteristics of one tissue can change during the course of disease progression. So as you can see with the liver shown at the bottom left, during the steps of fibrosis and cirrhosis, it's known that the environment becomes more stiff. So that's something that could potentially be modeled using. To dip into some specific examples, collaborators in the past have shown that certain cell lines behave differently depending on the stiffness of the gels that they're cultured with. So on the left-hand side here, we show some data from a collaborator at the University of Manchester. Showed that mesenchymal stem cells changed their morphology when cultured using different stiffness gels. You can see with increasing stiffness that the cell area, for one, increased, and also that the cells became less rounded, more eccentric, the lower stiffness to the higher stiffness. The example on the right shows a paper published by researchers at the University of Glasgow who were culturing pericytes. And they showed that using soft, stiff and rigid gels resulted in different differentiation characteristics of these cells. That's shown here, a graph by different expression of markers for neurogenesis on the left, chondrogenesis, middle, and osteogenesis on the right. So it was found that in soft gels, marker for neurogenesis dominates. Stiff gels, the marker for chondrogenesis dominates. Rigid gels, marker for osteogenesis was more abundant. And this work was also supported by metabolomic data. If you're interested in getting some more detail on this study, I think we have a linked to the publication website. So as well as tuning mechanical properties, Biogelx have a range of functional materials which include biomimetic peptide sequences, which have been identified from a range of extracellular matrix proteins. So probably the most well known of these is the RGD peptide sequence found in fibronectin, among other EM proteins. In addition to this, we have a product with the GFOGR sequence from collagen and IKVV and YIGSR, which are from proteins. In the images at right here, our collaborators found some cells preferred some of these functional materials. So the neurons in the dorsal root ganglia cells were cultured with RGD materials, and the same was true for the hepatocytes in the bottom left, whereas the fibroblasts in the bottom right preferred the GFOGR material. The key point really about these products is that all the peptides come from synthetic origins. It allows us to have good control over their characterization. They're also all functionalized with the FMOC anchor, which allows it to associate into the nanofibers discussed at the start with the F. I hope that gives some background on the technology which all of our products are based on, and I would like to take the opportunity now to move on to the bioinks which we've developed recently. Bioprinting really is an area of growing interest in recent years, and there's a range of applications that go from constructing very complex 3D structures with cells contained within them, or a process which can be used for the high throughput delivery of cell-laden material for well plate-based assays. And of course, there's a range of engineering techniques to execute a bioprinting project. A bioprinting application really requires some cooperation between this engineering side, so the hardware that's involved in bioprinting, with some materials chemistry, so the ink that you use, which will either carry cells within it or will be cell-friendly and allow cells to be seated on top of the structure that's printed. And of course, all of that has to cooperate with the biology, which will ultimately drive the application itself. So ultimately, really, the application is dictated by that biology, and from that you have to select a suitable printing method, which in turn demands certain properties of the ink itself. So starting in the middle example here with extrusion-based technologies, they're probably the most abundant in the research community at the moment. The setup for these techniques is relatively straightforward. Pressure is put on the bioink through either pneumatic or the piston system or screw system shown here. And the requirement on the ink here is that it should be relatively viscous, so that it will form a continuous filament when it's extruded under pressure. Depending on the application in mind, generally these bioinks should bear their own weight when they're printed, so they layer multiple layers on top of each other. Perhaps the example on the left is of inkjet bioprinting. There are other sort of droplet on demand type technologies that have similar ink requirements as the two shown here. They tend to be a slightly more advanced setup, potentially more expensive, but generally they allow very accurate deposition of small volume droplets of material. Examples here, that's induced either by a heater, by piezoelectric mechanism. Inkjet printing generally requires inks of lower viscosity, therefore you might need separate gelation steps after each layer is printed. So if you have multiple print heads in your printer, you can alternate between printing gel and crosslinker to form your gel. On the right hand side is probably the most high-tech hardware of these three examples with the laser-assisted droplet deposition. And this is another technology which promises very high accuracy. The ink for an application like this, for a printing method like this, be relatively low viscosity. For our bioink range, we've mostly focused on extrusion-based bioprinting. As I said, this tends to be the most abundant at the moment. We've developed viscous formulations of inks which can be printed without the need for a support material. Crucially, they'll bear their own weight, and when they're printed, they're partially cross-linked, which allows further cross-linking after printing by addition of excess cell culture media. This is partly achieved by introduction of a synthetic polymer with a high aspect ratio, acts as a thickening agent, but also we introduce a limited amount of cell culture media to the bioink to increase viscosity. One of the benefits, of course, of having this peptide-based powder is that these materials are all tunable in their viscosity and final stiffness. So for all, we have formulations highly optimized for extrusion-based printing. They can be tuned to various types of printing technology, and in fact, we're in the early stages of working with some collaborators, droplet on demand style printers. Compared to the hydrogel range that we discussed, the early stages of bioink preparation are quite similar. In this case, however, the powder is dissolved in a preparation solution that's supplied along with the bioink powder. So this is in place of the water used to make the gel. A limited volume of cell culture media is then added, which induces partial cross-linking, and this increases the viscosity to the level that allows bioprinting, building 3D structures which will bear their own weight. As I mentioned before, the printed structure then can be further cross-linked by addition. There's a short video here bioprinting of just a simple 3-layer lattice. Complex print, your design which builds up layer upon layer of bioink, give us a more complex structure. So this acts really as a demonstration. The inks bear their own weight and hold the character when they're an extra. So these products were all launched last year, and we currently have inks available based on the standard S formulation, as well as those with the biomimetic peptide sequences RGD, FOGR. The remaining functionalized products are still under development, so out for those later in the year. And all of these inks are available in a range of sizes. As I mentioned previously, the tunable nature of these materials, it's possible to optimize these for research needs. We're always happy to hear from collaborators or customers about new applications for our products. We're currently working with a range of collaborators and customers in the industry. Particularly, we're interested in applications including stem cell therapy, tissue engineering, and drug testing platforms. So if you have an application in mind and need some support, then please don't hesitate to get in touch. With that in mind, I'm very pleased to hand you over to speakers who are very application focused. So the first that we'll hear from is Dr. Jose Manuel Baena, who's the founder and CEO of Regemat, Breca Healthcare. After that, we'll hear from Mary Rodriguez, a research assistant at the platform for tissue engineering as University of Madrid. So all that remains for me to say is just thanks to the Biogelx team, to our collaborators whose work you can find through the case studies tab on our website, Business Review webinars for hosting it today. There will be an opportunity to answer questions at the end. If there's anything that we don't get around to covering, then please don't hesitate to get in touch, either through the website or by email at Biogelx. With that, I'll hand you on Dr. Jose Manuel.
Excellent. Thanks a lot. Thanks to the organizers, and also thanks to the participants for joining us today. I'm going to be talking a bit more from my background, from the industry point of view, from the engineering point of view. Just to present myself, I am a PhD in biomedicine, from background industrial engineering, also motorsport engineering. I founded 11 years ago one company that is called Breca Healthcare, and is implanting 3D printed implants. And with a collaboration with the University of Granada, with one of the groups I belong, we started developing a 3D printer in 2011, but not for printing metals or for printing PIC, as we were doing with the implant, but for printing biomaterials that biodegrade and cells. In 2011, we focused a lot in chondrocytes, but then quite early we decided to move to other applications. This is how I think my company is combined. Many people ask me why, if you are working with medical device, you start a company for doing tissues, for doing tissue engineering, and then even if we are able in an early future to create a functional tissue that can be implanted, we're going to need this temporal custom-made device that help us to keep the loads, to keep the shape, and also to integrate the in vitro created tissues in the defect of the patient. This was a patient from Barcelona we had many years ago with a zygomatic arch dissection, and then we were printing in titanium the medical device, and we were using the autologous scapula bone for the reconstruction of the maxillary. We are able just to print a biodegradable material that we can see even in the surgery theater with cells, and so we avoid the regulatory part. Then we can offer a better solutions. Then what we do is we think bioprinting is one part of the process of creating a living tissue, but we don't think it's the only part. We normally within the device we have this picture, this graphic, these two processes. The first one is the biofabrication, which you choose the right scaffold in terms of the right biomaterial, the right kind of geometry. We know in mechanobiology that the stress that we transfer to cells is a key factor to create one or another extracellular matrix. Then normally groups working with us, they want to work in the biomaterial of the scaffold, in the bioing with the cells, in the type of cells, and also in the other molecules that they use, because they also have activity on the final tissue. For this, we are the main customization biofabrication system company in the market. Then we create a specific biofabrication system, and we also work a lot in the bioreactor part and in creating under control and physiological conditions in the mechanical stimuli. Then we try to support groups that are the ones doing the research. As a company, we focus mainly in the development of the equipment, and one of the ones we are proud of them is the tissue engineering platform in the Hospital of La Paz. And they will be showing afterwards a key study, a specific study with the skin. Very fast, the part of what we are doing now in the clinical space, just to point the three main benefits of 3D printing in healthcare. This is a substrate procedure of a femoral component of a knee prosthesis. It's a substrate method, and with 3D printing this is an additive method, and we have mainly three advantages. We can create complex shapes We can create a mesh structure that for medical device and also for tissue engineering is very important. And the most important is, as an additive manufacturing procedure, we can add things during the procedure. In this specific case of bioprinting, we can add the cells and we can add another growth factors and other biomolecules that make that after bringing it in a bioreactor or even in vivo in some specific cases as to control injuries, then we can try to create a functional living tissue. Just to show you some specific cases, we have been implanting for quite a lot of time. We have like nearly 350 cases. We implant in many countries. Also, we do surgical guides. Very important when you want to do a reconstruction, even when you are using allografts or autologous tissues. This is very important to this specific case, craniosynostosis. We use surgical guides custom-made for reconstruction with the own bone of the patient. And you're going to have the presentation. Feel free to ask questions. I'm going to skip this very fast because I want to focus more on the biofabrication, part. Very important also now as an engineer, and I'm an engineer from background, we have the challenge is not just to simulating a static part, we have to simulate a living device, a material, a scaffold that is going to biodegrade, and also in many cases in cooperation with a medical device custom-made that is a mesh structure. It's also present a lot of challenge, and we think in the future there are going to be a lot of new engineers working and tissue engineers working on this. This is a quite recent case of the orbital reconstruction, and we just published a few weeks ago prosthesis, radius and semi-lunate prosthesis that was implanted in a patient. In the future, if we can put a solutions with the custom-made implants, and also, I will be talking about many solutions that we can do even in the short time, that is not like creating a heart or like creating a cornea, functional cornea. Is something that we can add a lot of value in the surgery solutions, even using the surgical guides, and even with materials that have been already approved, with thermoplastics, lactic acid, polycaprolactone. We print also now a lot of thermoplastic with hydroxyapatite, with magnesium. Then we have a lot of materials that are closer to the clinical application. Of course, we also work with centers developing innovative and futuristic materials. The problem with this is that in many cases they take more time. But I think you all agree with me that in the future, if you want to go through a surgery, you would prefer to have a biodegradation solution instead of having a metal implant in your body. This was the main thing. We started developing Regemat because my group, Professor Marchal in Granada, was working with contour sites from adipose tissue from Hoff's pad, and he found that after 2-3 weeks the cells either died or they differentiate. He was differentiating the cells from mesenchymal stem cells from adipose tissue, and then he asked me to develop as an engineer. Jose,
Hello, Jose, are you there? It appears we've lost audio with you, so if you could please try dialing back in, just while we dial him back in, if you bear with us.
hello, I'm here again. I think you have lost me. quite
Hi there,
difficult
Jose.
here because I am okay.
So we lost you at
I'm
slide
talking.
41, so I'll push you back there now, okay?
Okay. 41.
Wonderful.
Excellent. Then I was sorry for this technical problem. I was talking about bioprinting. For me, 3D printing, tissue engineering, and regenerative medicine. This is very important because I mean, when I see in media that we are printing like hairs or corneas, it's not true. What we are printing is a 3D structure with cells and other biomolecules, but this is not a tissue, and it's very important to work on the biofabrication side, but also on the bioreactor side. If we develop, that's why we develop a very adaptable and very customizable machines in order to be able to adapt to many different applications. Now, when we are mainly working on custom-made bioprinting system and bioreactor, but also we are now in production stage of a new system that we call F4Life, that is more specific and has some improvements. If you want more information on this and on the bioreactor, we have one patent on a bioreactor for the knee for creating mitochondrial tissues, but we are also producing bioreactors specific for arteries, and I think from our very engineering background in the company, we can also produce, and we are going to focus on producing specific bioreactors for a specific application. This is how I see this world. This is two-stage, as I said before. We have people working on the scaffold, people working on with the cells, with the biomolecules, also the maturation and the mechanical stimuli. And this is a two-block strategy. This is just to work on this on parallel, because the scaffold geometry is going to affect a lot the biodegradation time of the matrix, but also the stress, the load that are going to be transferred to the cells, the mechanical stimuli, and this is going to make the cells to produce one or other structural matrix. So we focus on bioinks. That is mainly the issue of the talk today. Then we have been trying a lot of bioinks. One of them was Biogelx. We like it because the printability is quite high. I mean, so in some cases, and also when we move to more extracellular matrix like biomaterials, the printability is not very high. Then you have to go to an indirect way of printing, that's creating a mold, a mesostructure, an inner mesostructure, and putting the extracellular matrix inside. But of course, if we want to take all the advantages of bioprinting, to print in a direct way is the most interesting. Then to have new innovative bioinks that can be printed directly, and it's the case of the G4, the biomaterial of Biogelx, also to have the available cell viability. Some cases we get some offer of getting new materials and they don't have a proper cell viability and proliferation study, and this is also very important. Also the biodegradation time. Of course, you can play with the biodegradation time with the mesostructure in the bioprinting if you are able to print directly, but it's also a very important factor. And also, if you want to, I mean, the most similar the biomaterial is to what cells found in vivo, the better, because then the cells are going to feel better and going to be happier. And also, for me, the most important, even more than mimicking the final biological structure of a tissue, for me is that the material can promote the creation of an extracellular matrix. Also, the price and scalability. Of course, in many cases, we are trying with material that the production is not very, very high. Then we have the problem of the price, and also we have the problem of the measures that we have in order to prove as a manufacturer that the material keep the conditions in all the production is complicated, and then if we vary a lot, mainly when we are using compressor for extrusion, if we have a material that is not well characterized, then we may have problems in the printing. And then also there is a lot of systems, not a lot of these new systems that are trying to prove the composition and the properties. Otherwise, we are going to have a lot of difference in one result from one day to other day, depending on the composition of the material. In 2013, we started the validation of the system. It was with the chondrocytes, I said before, with Professor Marchal. Then, I mean, we may think that printing cells is easy, but depending on the pressure, depending on the temperature, we have a lot of focus on thermoplastics because at the end of the day, we came from a company that is a medical device company, and we want to bring them. That is why also we try not to say too many things for the short term, because if I normally go to Congress in engineering, Congress in medical practice, and if I say them that I am printing bone, then the surgeons are going to complain, and they are right also, of course. short-term things, futuristic things are fine, but we have to keep the eyes on what we can bring to the clinical application now. We started many years ago also to keep helping to developing new bioinks, and we are in this industry that is growing. We saw a lot of new solutions, but I think we still have faced the challenge of better solutions, more solutions, and also to overcome the regulatory aspects and to be able to bring it to the clinical application. As a company, we like to adapt the systems. We think there is not the same system for cornea, bone, skin, for everything. This is not going to work. I mean, we work on the adaptation of the system, and also we define ourselves as a company as biofabrication strategies developer. Very important depending on this, because as I said before in my talk diagrams blog, it's very important to have the whole strategy on creating the tissue. We have also some publication on bioreactors part, mainly using ultrasound for applying local stress and also to monitor for a more futuristic quality control when we face the clinical application. We have very good partnerships like in over 30 countries. We are not a company that is producing 100 or 1,000 bioprinters a year. We are a company that are working closely with the users, trying to apply for funding with them, trying to bring this to the clinical application. This is one of the main collaboration we have for the clinical application with Dr. Carrillo, that is a great partner. Also, we customize the software, the hardware, and also the software. That is very important. And I think our software is one of the most versatile in the market. We try to improve the system, try to integrate it. We customize the most as we can the system to every application. This is also very interesting. Very key partnership that we have with Dr. Kamine in Sydney. And I mean, all the new things, again, it's very important when you define your strategy to talk to the engineers, to talk to the company that is developing. I wouldn't go for a commercial system just for doing some very basic. Before, few years ago, to publish something, it was quite easy, just putting bioprinting. Now it's about quality. Now it's about doing things different, and we implement a lot of different procedures that are published. This is a publication that I have for my PhD about the specific procedures that I'm going to skip because we lost a bit of time. And also, just to summarize, I think then in the next years, if we want to really make things that work and can be transferred to the clinical application, we are going to see a lot of indirect fabrication as well, not just everything. I mean, for me, biofabrication is you have to use it when it's adding value, and it's not always adding value. There is also another techniques, and you can also do a lot of things with the bioprinters and bioreactors with the indirect fabrication. We recently started a new department in order to supply all the researchers with everything that they need in the day-to-day, and also with a significant amount of biomaterials. The one of Biogelx, one of the key ones. We are based in Granada. We have some hours that we got. We are based in Granada in south Spain. If you come here, I invite you to see our new facility. That is quite a nice place to be, and I will be very happy to answer the questions after the talk of Mario. And here you have also some questions that you can answer, and you can give us a bit of feedback. Thanks a lot.
Thank you very much. So the first poll question we have is, has your organization considered to apply 3D bioprinting technology? Yes, we are working on 3D bioprinting project. Yes, we are setting up a 3D bioprinting research lab and start running a project shortly. We are evaluating the potential of 3D bioprinting technology for future applications. I'll give you a few seconds to vote. Now we move on to our next poll question. Is your organization interested in evaluating novel 3D bioprinting technologies? We would like to try novel bioink materials. We are looking for new bioprinter technologies. We are interested in both bioink and printer technologies. None of them. I am listening to the webinar to learn more about the new skin model. I'll give you a few seconds to answer that. Thank you very much. So as Jose mentioned, we now hand over to Mario.
Well, thank you very much. Thank you everyone for your attendance. I'm going to start my presentation. My section is going to talk about a small sample on how we can address an experimental framework regarding skin, in vitro skin analogs. These analogs can be addressed in many ways regarding the type of question we want to answer. So what I'm going to try to cover from some theoretical aspects to some specific experimental tips to work with this kind of culture. First of all, as we all know, although 2D cell culture systems have been played a key role in furthering our understanding in molecular signaling, in general, this kind of culture does not fulfill in vivo conditions. So 2D monolayers specifically lack in the environmental factors, mechanical forces, spatial orientation, many reasons. So we want another kind, or in the general flow is going through or moving on to another kind of culturing way. So bioengineered skin is becoming an essential tool to address many questions regarding cytotoxicity, cell viability, drug resistance, cancer progression, because it is proved experimentally that 3D conditions are more translatable to in vivo conditions than 2D culture. So since this information, with this information here, 3D cultures are more biochemically, mechanically, and structurally similar to in vivo skin. So this enable us to personalize our work, to contextualize this work properly, and make our experimental studies more translational. But how we build the skin in the laboratory? There are two different approaches here, like summarizing very much because there are a lot of information and ways to do it. But in general, there are two different approaches. The scaffold-free approach, which consists in cell aggregates produced by the self-assembly of one or more cell types. For example, spheroids or organoids, culture in gelatin or any other matrix, but with no, this matrix is not necessarily, is not an essential condition. So these cells self-organize alone. This kind of approach is attractive because it has low degeneration costs and a high reproducibility. You can have a lot of spheroids and organoids growing and expanding in vitro. So you're gonna have a lot of experimental substrate, if you call it that, to work with. The other way around, we have the most typical one, the scaffolded approach, using both natural biopolymers such collagen, fibrin, fibronectin, and whatever, which are more degradable, more biocompatible, and more similar to in vivo condition, but they have poor mechanical properties. So since they have poor mechanical properties, there are another counterpart, which is the synthetic biopolymers. These polymers have better properties in terms of physics, the mechanical forces, and resistance. And maybe they could have conductivity or other features, but in some cases they're not as biocompatible or biodegradable like the natural ones. So the combination of both leads us to which we Chris addressed already, which is called bioinks, and we were going to review them in the following slide. So regarding all of that, as a summary, type 1 collagen is still the first option for scaffolding in vitro skin. It has very poor properties in terms of mechanical forces, but it's the more common compound in the extracellular matrix. So usually people use this one to construct the skin in vitro. So the design of bioinks are the difference between these materials and bioinks is bioinks are tailored to be printed, to be compatible with that 3D bioprinted systems. The previous materials have been used in classical skin tissue engineering approaches, but regarding bioprinting, we need bioinks, because it's more suitable. So the main challenge is to get rid of the previous limitations and to move on to most personalized and specific materials to design tissue in vitro. So, in general, these are the ingredients, the experimental ingredients we're gonna use in the experiment, the little experiment. The cell lines chosen has been human dermal fibroblasts because they are the standard. Is the most common cell type you get in a biopsy. And on the other hand, we have HACATs, immortalized keratinocytes. We used this one, and I'm addressing this question because it is important to define which kind of cell you're going to use regarding your experiment, because it's going to define culture conditions, time of culturing, and so on. So HACATs is not the standard because you are not getting immortalized keratinocytes from a body in a biopsy. But the thing is, when you're culturing keratinocytes in vitro, they need a feeder layer, and it's a complicated culture. So we decide to go for a type of keratinocyte that can proliferate and differentiate in vitro, but does not need a feeder layer, because we had at that time a little amount of bioink, so we just went for a more secure movement here. So yeah, this here we have the general scheme to culture in vitro skin. We have two different phases. One is the submerged stage, when you construct the dermis with the fibroblast. You just mix both things, because I just read a question about this. So you mix these things, fibroblast and collagen, or the material you're using to construct the dermis. You leave that in culture, and then you add the fibroblast. You leave the fibroblast to attach to the dermis, and then you go on to the airlift culture in order to ensure the differentiation of the epidermis strata, all the different strata we have in the epidermis. So yeah, our experimental framework then is going to be so simple, because we have a little amount of bioink, and we cannot talk about specific details regarding a possible publication here. So we're gonna go over this really quickly. We compared the standard, the type 1 collagen in a high concentration. The usual concentration used in collagen varies from a paper to another one. So in my opinion, a good concentration could be a 0.6 or 0.8. Yeah, so we went for the collagen type 1 from Corning in high concentration, rat tail, to compare with the Guy Fauger bioink from Biogelx, which is a bioink based in collagen. It's a collagen functionalized bioink. We want to test how in a really preliminary stage of our work, how cells behave when in contact with the collagen and when in contact with the bioink, and how we evaluate the results, most importantly, which tests we perform. So here we have like a rough comparison. These are in the first week of the culture. Usually the culture of the skin takes around 21 days to fully develop a full thickness skin. But in our case, we wanted to address how the critical stages, those which are in the beginning when the cells establish themselves inside the collagen, and they are attached one to another. In those critical stages, we wanted to address how our cells behave in contact of both materials. So we have here different clear differences between how the structure, we can see the laminin structure and the preliminary stratum basale of the epidermis, and underneath the epidermis in the case of the G. Fourier Biogelx. And then in the type 1 collagen, we just obtain a dermis without any further structure, no epidermis or not thinner ones. So these differences are noticeable after a couple of days, more or less, in the culture. So we stick to that time and perform also a cell proliferation assay, marking KI67. KI67 is a marker for cell proliferation. So we wanted to address how the cells attached, which is in this case keratinocytes, how well they attach to the epidermis and if they are performing a healthy division and proliferation. And we can see some region in the G. Fourier Biogelx-based equivalent that showed a tinted positive cells on top of the dermis. So in comparison with the collagen, it shows a clear difference between both cases here. So the cell proliferation was healthier, let's say, because these all results are really preliminary. Once we complete this first part, and we tested it in a small P24 culture plate. We moved to a bigger insert to try to print a larger skin portion. So here we see the results, the preliminary results of using G. Fourier, which is a polarized dermis with a really thin laminin on top with a few cells. There are few cells because the incubation time we took as a reference was insufficient. It's not this is not due to the bioinks, but the incubation time. So moving on, the cell proliferation showed up also active cells when using G. Fourier in no time in the culture, practically less than 48 hours. In the last case, we perform a laminin immunochemistry because laminin is a signal that a keratinocyte attached successfully to the dermis and start the procedure of proliferation and establishing incipient preliminary epidermis. So here we have positive results for laminin using G. Fourier as well, when we didn't get that using the collagen in this time. So the attachment is faster and the cell proliferation is of course faster as well. But this is really preliminary. You need to, in order to address a complete differentiation, we have the conclusions here. we would like to perform with more bioink a full culture, which means leaving the inserts 21 days in the incubator with, of course, often changes of media. But in order to test those, we could go for more markers to test the complete development of the skin. For example, cytokeratins 1 and 14 to assess them if our epidermis is mature or not. Laminin, involucrin, maintaining hematoxylin, of course, for the structure. Another markers, I don't know, for like filaggrin as well is useful if you want to test the different strata. So here, this is the main conclusion. G. Fogger have shown a more like compatibility. This is not compatibility, but more harmony with the cells. Cell activity is higher in G. Fogger-based skin inserts, and of course, in order to fully give an experimental closed framework, we would like to extend our culture to 21 days in order to see how fast the different culturing goes, comparing collagen and G. Fogger or not. And key future checkpoints regarding all this, of course, the standardization for a vascular system in this insert would be ideal, but it's not actually well established right now. Integrating immune cells successfully would be interesting regarding if we want to design a platform, for example, to test immunotherapy prior to clinical trial. Combining bioprinting with other tissue engineering techniques to increase the individuality of the obtained equivalent. It is important to keep that bioprinting offers a lot of advantages, but it is high cost right now. So it is important to compare all the time this system with the manual casting or another experimental approaches to make sure that we have all the clues on all the experimental hints to say that bioprinting is better. Assessing legal framework and quality standard, if we want to work on this on like in a standardized environment. And is the last one, a more frequent and efficient collaboration between enterprises, healthcare, and provider, because right now, at least in Spain, this is not happening correctly. So we need more collaboration if we want to implement bioprinting in hospitals and closer to the clinic. So thank you very much. If you have any questions, please just let me know.
Thank you very much. We now move to our two final poll questions of the evening. The poll questions are: which experimental design will be more suitable if a high throughput analysis is required? Scaffold-free in vitro skin analogs such as organoids. In vitro full thickness skin equivalent. Oh, sorry, continue.
Yeah. No, sorry. I was, you can continue, Ara, thank you.
In vitro full thickness skin equivalent built out of collagen, since it is considered the standard option, or none of the above. We'll give you some seconds to answer that. And the final one we have today is: which marker would you choose to evaluate the epidermis development in a full thickness skin equivalent? A. Cytokeratin 1. B. Cytokeratin 14. C. Involucrin. D. A, B, and C. Or E. None of the above. I'll give you a short moment to answer that one as well. So unfortunately, that's all the time we have for today, but that just leaves me to thank Chris, Jose, and Mario for what was a great presentation, and to Biogelx for sponsoring this session. To the attendees, if your questions weren't answered today, don't worry. The team will be back in contact with you, so please do keep those questions coming in and you'll be answered by email. You'll also receive an email telling you how you can access the on-demand version of this webinar, or you can access this through our website, which is www.business-review-webinars.com. We look forward to sharing further webinars with you, so please do keep an eye out on the website just mentioned, and follow us on Twitter @BRWebinars for daily updates, and join our LinkedIn group, Business Review Webinars. Thank you once again, and I hope you all have a nice day.